Ladies and gentlemen, it's my pleasure to talk today about advances in-situ metrology of UV LED structures in MOCVD. This work is a collaboration between the Ferdinand-Braun-Institut and LayTec. My name is Kolja Haberland, and it's my pleasure to present our results to you on behalf of my co-authors. Here is the outline of my talk. After a short introduction, I will talk about the in-situ metrology for UV LED growth, and I will mainly highlight the 280 nanometer reflectance measurement. And finally, I will give a summary. Let me at first briefly show you what LayTec is doing. We are a provider of integrated optical metrology that is used for process control in various industries and markets. Our tools are used to control the deposition of LED structures as well as laser structures, when functional layers are coated on glass, in the production of power devices, and in photovoltaics. In this talk, we look at the application to LED structures, and in particular at the production of UV LEDs. Let us have a look at a typical layer structure that is used for a deep UV LED. As you can see, it's a very complex structure that consists of many layers. There are a lot of challenges in both growing these structures and doing the in-situ metrology. One is the very high growth temperature of up to 1500 degrees C. Another is that both substrate and buffer material are very much transparent, so that the wafer temperature measurement is very challenging. During the hetero growth, we see a rather large lattice mismatch and thermal mismatch that leads to very high wafer bow effects. We also see growth on pattern substrates that have very low reflectance, such as nano PSS material. And we have very long growth zones with a very high aluminum content and doping levels, and the layer stack is sometimes thicker than 3 micrometer. On the other hand, we have very thin layers in the stack, such as the quantum wells, the superlattice, or the electron blocking layer, so there's a lot of challenges in one structure. The production of semiconductor devices such as UV LEDs is a complex process. We see a schematic here of the manufacturing chain starting with a substrate. In front end, one very important step is the epitaxy, where the layer stack of this LED structure is grown, and here the in-situ metrology is used to monitor and control the growth. That helps to predict some of the device performance already very early in the manufacturing chain. That is a good idea because there are many more steps coming, and you really want to make sure that everything is in spec here in front end. Additional LayTec metrology can be used later in the process when the wafer are leaving the MOCVD system. You can use our mapping tools to characterize uniformity, and then the wafers will be further processed. We'll see dies on wafers, we'll see the back end with substrate separation and die singulation, packaging, and in the end there are finally the LEDs. So it is a good idea to use in-situ metrology to understand the growth process and control what's going on inside the MOCVD chamber. UV LEDs are grown by MOCVD in such a system. Wafers are loaded and the recipe controls the layer stack. The in-situ metrology tool is mounted inside the MOCVD system, right on the reactor lid, looking through a viewport into the reaction chamber and allowing to characterize the wafers at the time of growth in real time. A lot of data is provided, and the data are made available over an interface to the MOCVD system so that closed loop control is possible. Usually the measurements are performed for wafer and pocket temperature, for layer thickness and growth rate, wafer curvature, ternary composition, and surface morphology. It's also possible to provide information on the uniformity across the wafers. And that obviously helps in producing better UV LEDs on the long run. The schematic layer structure of a UV LED structure is shown here. This is the growth direction from the substrate to the contact layer. The data we present here have been obtained in an Extron closed coupled showerhead system on a 6 by 2 inch configuration. The viewports here in the lid allow access to all 6 wafers, and so all 6 wafers have been measured simultaneously and were characterized and measured individually. The growth of the aluminum nitride template on Sapphire has been done in the second run in a different MOCVD system. So this is a two-stage MOCVD process here. As already mentioned, the primary measurements are the temperature, the reflectance, and the curvature. Reflectance is measured at 4 wavelengths at 950 nanometer, that is infrared at 633 nanometer, that is red at 405 nanometer, which is a blue wavelength, and at 280 nanometer in the UV. The data are shown here as an example. The growth time is vertical. Normally we like to look at the data rather this way, with having the growth time horizontally. Let me at first highlight why 280 nanometer is a very useful wavelength for monitoring of UV LED structures. Here on the left-hand side, you see some data measured during growth of a rather thin layer. At 950 nanometer, we see not much modulation during the growth of that layer because the layer is rather thin compared to the wavelengths. With 633 nanometers, we already see that there's much more of an oscillation visible. With 405 nanometer, we can clearly see the oscillation, and that is good enough to allow a growth rate measurement for that kind of layer. But we see with 280 nanometer, due to the shorter wavelengths, we see more periods, we see a higher amplitude, so our sensitivity to that kind of layer is much better with 280 nanometer. That's why this wavelength is suited for growth rate fitting on rather thin layers, and it also has a very high sensitivity to roughness and surface morphology effects. So it's a really useful add-on to the in-situ metrology. Now let us look in more detail at the application of the 280 nanometer reflectance measurement. These are the in-situ data measured during the growth of a 255 nanometer UVC LED that was grown on an aluminum nitride high temperature anneal template. This is a whole growth run, started from heating through the aluminum nitride buffer growth. There is a growth of an N-doped aluminum gallium nitride buffer with different compositions. Here is the active zone with the quantum wells. This is the p-side contact layer, and here the structure is cooled down. The blue curve is the reflectance at 400 nanometer, the green curve is the curvature, and the red curve is the temperature. PL data are provided to show that the LED in the end emitted at 252 nanometers, so very close to the target. If we look at these data, especially at the reflectance curve, everything looks nice. We see nice Fabry-Pérot oscillations with the temperature changes, the amplitude changes, and the growth rate are different, but we see nice oscillations, and there's no indication something went wrong. Really? So let us look in more detail. This again is the reflectance at 405 nanometer, showing nice sinusoidal Fabry-Pérot oscillations, indicating ideal to the growth of a thick layer. When we look at the 280 nanometer data that were obtained at the same time, okay, we see the quantum wells showing up here as the kings on the curve, but we also see that in the second part of the aluminum gallium nitride layer, the oscillations do not look sinusoidal anymore. It's nice here, but here it's different. And that looks rather like a superposition of more than one Fabry-Pérot oscillation. So this could indicate that this is not a bulk layer, but something like an unwanted superlattice. In order to analyze and understand this, we can simulate the 280 nanometer data from the database and compare to the measurement. This is the result of a simulation with the assumption that the first part of the AlGaN layer is a single layer, a bulk layer that has been grown with a constant growth rate, and that the second part of the AlGaN layer is actually a superlattice of AlGaN and AlGaN with periodic composition variations or fluctuations. And when we compare the simulation, shown here in violet, with the measurement in red, we see that it nicely agrees with the measurement, so we can assume that there is indeed a periodic composition variation in the aluminum gallium nitride. And in order to confirm this, TEM measurements has been performed. So here is the TEM picture on the right-hand side. We can clearly identify our layers. The bottom, the aluminum nitride buffer corresponding to these Fabry-Pro oscillations. Then the first part of the aluminum gallium nitride layer, which corresponds to this part with the nice sinusoidal oscillations. And finally, the second part of the AlGaN layer that corresponds to the part where the oscillations look different. And you can clearly see here the superlattice, the unintentional superlattice. And so this is in agreement with the in-situ data. And now we need to find out what is actually the reason for this. So the origin for the AlGaN composition fluctuations was eventually found in a defective gallium pressure controller. The exchange of that pressure controller solved the issue, and the growth run was repeated with a different pressure controller. There was no sign of any superlattice anymore, neither in TEM nor in the 280 nanometer reflectance. We see the data here, the repeated growth run. Here is the AlGaN layer, and we see also in the second part, nice sinusoidal oscillations. And here the comparison of the TEM picture before the exchange and after the stripes, the superlattice is gone. So this was a good example to show how the 280 nanometer reflectance proves to be very sensitive to thin layer effects and much more sensitive than the 405 nanometer reflectance. So let me summarize my talk. I've shown you that UV LEDs are complex device structures and that especially the epitaxial growth in an MOCVD system is very challenging. I've also shown you that optical in-situ metrology helps to address some of these challenges by providing important layer information such as temperature, reflectance, and curvature already during the MOVB process. Reflectometry at 280 nanometers in particular is very useful as it allows thickness measurement for rather thin layers. It provides a high sensitivity to morphology and roughness and also for variation of the AlGaN composition. I've shown you that an unintentional AlGaN composition superlattice that was due to a gallium pressure fluctuation was discovered by looking at the 280 nanometer in situ data, and that these findings were confirmed by TEM. So the bottom line is in situ metrology substantially helps to understand and control the MOCVD process. Finally, I would like to gratefully acknowledge financial support by the German government in the Advanced UV for Life Consortium. Thank you very much for your attention, and I'm happy to answer questions.